Hi, I'm Mark Barsamian. In this video, we'll learn about what's called the derivative of a function, and we'll do some examples involving computing derivatives for various polynomial functions. This material is from the book section 2.4, Rates of Change. More specifically, the reading is from the middle of page 135 to the middle of page 137, example 4. And the corresponding homework is this homework 26, involving computing what's called f prime for a polynomial function. It's 4 exercises from section 2.4. So as I said, we'll be learning about the derivative of a function, and we'll be discussing examples involving computing derivatives of polynomial functions. In the previous video, we discussed what was called the instantaneous rate of change of a function and the tangent line to the graph of a function. They were defined with these definitions. The instantaneous rate of change was denoted by this symbol, and it means the number that you get from doing this calculation. And the line that's tangent to the graph of a function at x equals a means the line that has these two properties. The line contains this particular point, and the line has slope that's equal to the number that is the instantaneous rate of change. I want to focus on this expression. This f prime parentheses a equals this limit. Now in this expression, the symbol a represents a number, and the symbol f represents a function, and this whole symbol, f prime parentheses a, represents a number. It's a number that's the slope of a line tangent to the graph of a function. And you find this number by finding this limit. And this number, this symbol, is spoken the derivative of f at a. Now consider replacing the number with a variable x. Then this expression would not represent a number, but it would represent a function of x. That function is called the derivative of f. So here's the definition. We have this symbol. It's spoken f prime of x, also spoken the derivative of f of x. And what it means is this function. That is, you have that messy limit expression, and instead of an actual number a in there, you have a variable x. Now, what is this used for? Well, if you have this expression and you actually substitute in a number x equals a into that derivative function f prime of x, then the resulting thing would be denoted f prime parentheses a, and that could be interpreted as before, the slope of a tangent line, or that's also called the slope of the graph, also called the instantaneous rate of change of the function at x equals a. And in the previous video, we discussed situations where the function f of x is a position function for a moving object. Then this number f prime parentheses a is what's called the velocity of the object at that time. So that's the idea of the derivative function and what you can use it for. A couple of things are important to note. You'll often hear things like this. You'll hear this sentence: the derivative is the slope of the tangent line. This is actually wrong. The slope of the tangent line is a number. The derivative is a function, not a number. They're not the same thing. So a better way of thinking about the derivative is this. The derivative is a function that can be used to find the slope of tangent lines. So the derivative itself is not the slope of the tangent line. In today's video, we're going to be computing derivatives of polynomial functions, and we're going to be using the definition of the derivative presented 2 pages ago. That means that given a function f of x, we're going to be building the expression for this limit that's described in the definition of the derivative. And then we're going to be using the properties of limits to compute that limit. And the result of that limit will be a function that is the derivative f prime of x. Now, computing the derivative f prime of x using the definition of the derivative is difficult and it's messy. Now, some of you may have studied calculus before and you know about an easier way of finding derivatives, so-called derivative rules. We'll be learning about derivative rules in this course as well, but not yet. Right now we're going to focus on finding derivatives using the definition of the derivative. That's the harder, messier method. In section 2.4 of the book, the authors present a 4-step process for finding the derivative using the definition of the derivative. And here's their process. In the homework exercises for homework 26, which this video accompanies, you're actually asked to find derivatives using this 4-step process. I don't actually like the book's use of the 4-step process because I feel that it obscures what I think is the most important concept of the first month of the course. When can one cancel terms and why? For that reason, I'm going to use a different procedure when I compute derivatives using the definition of the derivative. It's this procedure here in this green box. And its emphasis is on being very clear about what things mean and what you're going to be doing. So the first step in a solution will be to present the goal. So you're going to write down that you're going to find this thing. And then get the parts that you're going to need to build that expression. Use those parts to build that expression and compute it using the properties of limits. Not the shortcut derivative rules, but actually the properties of limits. And all along the way, explain clearly. In particular, point out limits that are indeterminate forms, because that's very important. And if cancellation is done, explain clearly why it's justified. All right, here's our first example. This is similar to one of your homework exercises. F of x is this quadratic polynomial. Now we're supposed to find f prime using the definition of the derivative, and then find these things. And then finally illustrate those results using a given graph. Now, as I said before, in the book's wording of this problem, or problems like it, they have a question A that's to use the 4-step process to find f prime of x. I won't be using their 4-step process, I'll be using my own process. Now let's go back up and look at that process. That's what we need to do. We need to present the goal, get the parts, build the limit and compute it, and all along the way, explain clearly. So our goal. So we need to find that limit. Now notice that this is actually an indeterminate form. If we were to substitute in h equals 0, we would get f of x minus f of x in the numerator. That would be 0 in the numerator. And we would get 0 in the denominator. So that tells us that we can't do this limit by simply plugging in h equals 0 right now, because we would get 0 over 0. And remember, when computing limits, if you get 0 over 0, you can't do the limit that way. You have to find some other way. So what do we do? Well, again, we have this process. We need to get the parts that we're going to need to build that expression. So we need f of x plus h. Now there's our function f of x. We'll do what we have done before for problems like this. we'll get the empty version. So there is our very messy result of finding f of x plus h. F of x plus h is this whole messy expression. Now, what's next? We've got the parts. We presented our goal. We got the parts that we needed. So we have to build the limit expression and compute it. That is, we need to build this. So our expression that we need to build has an f of x plus h there. It has an f of x there. So we need to go get the expressions for those two things. Well, f of x is easy. That's there. We've taken the formula for f of x and we've put it into that limit expression. Now we need to go get the expression that we just built for f of x plus h, and we need to put it here. So that's that messy expression that we got when we built f of x plus h. That was the parts that we needed. So we have built the limit expression. Now we need to compute it. Well, the first thing that we can do is we notice that some things can be canceled. Notice that there's a minus 3x squared here that's going to cancel that minus 3x squared. And there's a plus 12x here that's going to cancel that 12x. And there's a plus 15 here that's going to cancel that 15. So we can cancel those terms just because it's arithmetic. So it's very important to explain the steps and to show the before and the after steps clearly. In other words, we're going to cancel those terms. It's worth showing what you get after you do that. Show a new line that shows the result of that canceling. And notice that my new line still has this limit as h approaches 0 parked in front of it. Now, it looks like we can cancel some h's here, but as has happened many times in this course, we have to be very careful and very clear about our cancellation. Now, I want to set the cancellation up so it's very obvious what it is that we're canceling. So in order to do that, I'm going to factor out an h in the numerator. We show the result of factoring out that h, and this is a very useful step to have because we can see clearly that this is an indeterminate form, because if we were to substitute in h equals 0 right now, we would get 0 over 0. But hey, remember that we know something about h. We know that h is approaching 0. And that tells us that h is not 0. So since h is not 0, we can cancel that h over h. So that's very important. It's the most important step of the first month of the course. So let's explain it in words. Now, remember, that's the most important step of the first month of the course. So it's important to show the before and the after. So we have this new line that shows what we get after we do that cancellation. Notice we still have parked in front this limit expression. We have not been able to do the limit yet. We're just simplifying the thing inside the limit. Hey, look at this. We no longer have an indeterminate form. And in fact, look at this. This expression is a polynomial. It's a polynomial in the variable h, not the variable x. H is the thing that's varying. Now, we're taking the limit of a polynomial, so we know that we have this theorem 3 that tells us that we can just substitute in h equals 0. There's our result. Notice that once we use theorem 3, there's no longer a limit expression in front of this. We've done the limit, and we end up with an expression that does not have the limit symbol in front. So what we have just found is that this thing, f prime of x, is this function. So that's our answer to question A. Question A was to find f prime using the definition of the derivative, and that's what we did. Now our job is to do these things. Find f prime parentheses negative 2, f prime parentheses 0, f prime parentheses 2, f prime parentheses 4. Now what does that mean? That symbol means to substitute x equals negative 2 into the formula for f prime of x. So there's our formula for f prime of x. We have to substitute in x equals minus 2. Let's start by getting the empty version of f prime of x. So the result is that f prime parentheses negative 2 equals 24. In question C, we're supposed to find f prime parentheses 0. The result is f prime parentheses 0 is 12. Again, we used the empty version. We substituted in x equals 0. Question D, we're supposed to find f prime parentheses 2. Notice that we get that f prime parentheses 2 is the number 0. Finally, question E, we're supposed to find f prime parentheses 4. So the result is that f prime parentheses 4 is the number negative 12. Okay, now what's next? In question F, we're supposed to illustrate those results using a given graph of f. How are we supposed to illustrate these results? What do these results have to do with the graph? We have this result that f prime parentheses negative 2 is the number 24. We have this result that f prime parentheses 0 is 12. And this result, f prime parentheses 2 is the number 0. And this result, f prime parentheses 4 is the number negative 12. We have those four results. What do those have to do with the graph? There's the graph of f of x. So again, what do these results have to do with that graph? How do we illustrate those results in this graph? Well, to answer that, let's go back up and look again at the definition of the derivative. The definition of the derivative was this thing. We found that formula. We found that f prime of x was minus 6x plus 12. That was a function. But what's it used for? Well, when you actually substitute a number into that formula for f prime of x, the resulting number, f prime parentheses a, can be interpreted as the slope of a line tangent to the graph of f. So those things that we computed in parts B, C, D, E of the problem, those numbers that we got were numbers that are slopes of tangent lines. So those four numbers are slopes of four tangent lines. So to illustrate those results, we should draw those four tangent lines and label them. So there's the graph. Which tangent lines do we need to draw? Well, this number is the slope of the line that's tangent to the graph at x equals -2. So we have to draw the line tangent to the graph at x equals -2. How do we do that? Well, we find the point on the graph that has x coordinate -2, and we draw a tangent line. And what do we do to illustrate more clearly what this has to do with our previous solutions? Well, we should indicate that the slope of this line is 24. Go back up and look at our result again. We found this result, f prime parentheses -2, is 24. That tells us that the slope of that tangent line is 24. Now what about our next result? This result has to do with the slope of the line that's tangent to the graph at x equals 0. This result tells us that line has slope 12. So we need to draw that line and label it. Here it's a little bit clearer that these are the tangent lines at x equals -2 and at x equals 0. Let's go back up and look at our next result. Our next result was this one. That tells us that the line that's tangent to the graph at x equals 2 has a slope that's the number 0. So that tangent line has a slope that's the number 0. That tells us that the tangent line is horizontal. Now finally, our last result. Our last result was this one. That tells us that the line that's tangent to the graph at x equals 4 has a slope that's m equals -12. So we draw the tangent line and we label its slope. Notice that that tangent line has a slope that's negative because the tangent line is tilting down. So that's the end of example 1. Example 2 is similar to another one of your homework exercises. In this example, f of x is this function, which is a polynomial function as well. So we have the same exact questions. So here we go. So the same thing we did in the previous problem. Start by saying what we need to do. Then we need to get the parts. So the thing that we need, the part that's difficult, is f of x plus h. So how do we do that? Well, let's get the empty version of f of x. So there's our expression for f of x plus h. It equals that messy expression. Now the next thing is we put the parts into that limit expression and compute the limit. So there we have put in our expressions. Notice what we did. We replaced this whole expression with this expression. So there's no longer an f in our limit expression. It's just this, this red circled thing. And we also replaced f of x with the expression for f of x. We took that whole symbol out and we replaced it with this thing. There's no f anymore. Now notice both of these limits are indeterminate forms. Because if we substitute in h equals 0, we would get 0 over 0. Remember that when you have an indeterminate form, that tells you that you can't substitute in h equals 0, or can't substitute in whatever the number is where you're computing the limit. You have to find a different way. The different way is to use the properties of limits. First thing we can do is we can cancel using arithmetic. Notice we still have an indeterminate form, but we can see that it's indeterminate because of that h over h. Here's that important step. We know that we can cancel the h over h because we know that h is not 0. So here, again, notice that I show the result of the cancellation. I still have a limit parked in front of my expression. Now, this limit, the limit of a constant, is just the constant. So we have found that f prime of x is the number 5. Well, that's kind of strange. Let's go on to the next parts. So f prime parentheses negative 2 is 5. That's the way it's going to go for all of the other ones as well. So we have these 4 results. The result of the derivative in each case turned out to just be the number 5. Now, question F is to illustrate those 4 results using the given graph of the function. So let's go have a look at the graph of the function. So this is the graph of y equals 5x minus 7. Looks like I've made a mistake in plotting this graph. I've got the x-intercept in the wrong place. So the graph should look like that. The y-intercept should be below the x-axis. Our results are about slopes of tangent lines. The tangent line at x equals minus 2 has slope m equals 5. The tangent line at x equals 0 has slope m equals 5. The tangent line at x equals 2 has slope 5. You get the idea. So these results make sense because the graph of the function is a straight line with slope m equals 5. So it makes sense that all of the tangent lines have slope 5. That's the end of example 2. Example 3 is similar to your exercise 2.4 number 19. It deals with this function, f of x equals 7, which is a polynomial. Now, we have the same exact questions, so here we go. So there's our usual opening of the solution. We start by saying what we are going to be doing. Now let's get the parts. So what are the parts we need? Well, we need this thing. We need our f of x plus h. So let's start by writing down f of x. Now what about the empty version? Well, we just get rid of all the x's and replace them with empty parentheses. Notice that there are no parentheses on the right side of the equal sign because there were no x's on the right side of the equal sign to begin with. Now we plug x plus h into those parentheses. So there's our f of x plus h. It's just the number 7. So now we're going to put the parts together into this expression and use the properties of limits to find that limit. So there's our limit expression. Now we need to build this expression. So we need to go get our expression that we found for f of x plus h and put it there. That is this thing. F of x plus h is the number 7. And then we need to go get the formula for f of x and put it there. Well, remember, f of x is 7 as well. F of x is there. Now we can use arithmetic to cancel. Now, it seems like we should just be able to say that 0 over h is 0. But that's actually subtle, because what do we know about h? If we didn't know anything about h, we wouldn't know that 0 over h is 0. 0 over 5 is 0, 0 over 13 is 0, but 0 over 0 is not 0. It's undefined. So we would like to simplify this. We would like to replace 0 over h with just the number 0, but we have to say why we can do that. It comes down to, again, the fact that we know that h is not 0. That's why we can say that 0 over h is 0. So we show the result of that. We still have the limit expression sitting in front, and this limit we can compute. The limit of a constant is just the constant. So we found that f prime of x is 0. Now in parts b, c, d, e, we have to find f prime at -2, 0, 2, and 4. We can do all those at once. All of those derivatives at those particular x values are just going to be the number 4. So in question F, let's illustrate this with a graph. So let's go down and look at the graph. Now here again, I made a mistake when I made this. Let's see, let me clean this up. If this is the x-axis, and this is the y-axis, then this line would have equation y equals 7, f of x equals 7. Now, how do we illustrate our results on this graph? Let me make the graph a little bit fatter. Let's go see our results. This tells us that the tangent lines at those 4 x values, x equals -2, 0, 2, and 4, should all have slope 0. So that's the end of the example, and that's the end of the video. Thank you.